Hi there! Welcome to General Physics 1. Our lesson for this week is about Newton's laws of motion. At the end of this presentation, you will be able to apply Newton's first law to obtain quantitative and qualitative conclusions about the contact and non-contact forces acting on a body in equilibrium. Second, apply Newton's second law and kinematics to obtain quantitative and qualitative conclusions about the velocity and acceleration of one or more bodies and the contact and non-contact forces acting on one or more bodies. Third, analyze the effect of fluid resistance on moving object. And finally, solve problems using Newton's laws of motion. Previously, we learned that mechanics is the branch of physics concerned with the study of motion and what produces and affects it. Also, you've seen in the previous lessons how to use the language and mathematics of kinematics to describe motion in one or two dimensions like speed, velocity, acceleration, free fall, and projectile motion. But what causes bodies to move the way they do? For example, why is it harder to control a car on a wet surface than on a dry concrete? The answers to these similar questions take us into the subject of dynamics, the relationship of motion to the forces that cause it. In this lesson, we will use two new concepts, force and mass, to analyze the principles of dynamics. These principles were clearly stated by Sir Isaac Newton in his laws of motion. More than 2,000 years ago, the ancient Greek scientists were familiar of the ideas in physics that we study today. Probably the first to seriously study motion was Aristotle. Aristotle, the foremost Greek scientist, studied motion and divided it into two types, natural motion and violent motion. He coined that all objects seek their natural state of rest, such as boulders on the ground, and smoke high in the air like the clouds. These motions were considered natural, not caused by forces. Most thinkers before 1500s considered it obvious that Earth must be in its natural resting place, and a force large enough to move it was unthinkable. Hence, Earth did not move. Violent motion, on the other hand, was imposed motion. It was the result of forces that pushed or pulled. Objects in their natural resting places could not move by themselves, so violent motion was imparted to objects in order to move. Thus, Aristotle deduced that moving objects must necessarily have forces exerted on them to keep moving. Pushing or pulling an object causes a natural motion or violent motion. If cause is removed by not pushing, then object returns to natural state and stops moving. The astronomer Nicholas Copernicus formulated the theory of the moving Earth. This idea was extremely controversial at that time. People preferred to believe that Earth was at the center of the universe. Copernicus reasoned that the simplest way to interpret astronomical observations was to assume that Earth and the other planets move around the Sun. Galileo, the foremost scientist of the late Renaissance Italy, was outspoken in his support of Copernicus. One of Galileo's great contributions to physics was demolishing the notion that a force is necessary to keep an object moving. He tested his idea by rolling a ball using two inclined planes facing each other. He found out that a ball released to roll down on one plane would roll up to the other to reach nearly the same height. The ball tended to attain the same height even when the second plane was longer and inclined at a smaller angle than the first plane. If the angle of incline of the second plane were reduced to zero, so that the plane was perfectly horizontal, only friction would keep it from rolling forever. It was not the nature of the ball to come to rest as Aristotle had claimed. Galileo stated that if friction were entirely absent, a ball moving horizontally would move forever. No push or pull would be required to keep it moving once it is set in motion. Galileo argued that only when friction is present, as it usually is a force needed to keep an object moving. Friction is the name given to the force that acts between materials that touch as they move past each other. Friction is caused by the irregularities in the surfaces of objects that are touching. Even very smooth surfaces have microscopic irregularities that obstruct motion. Galileo stated that this tendency of a moving body to keep moving is natural and that every material object resists changes to its state of motion. The property of a body to resist changes in its state of motion is called inertia. Newton did not derive the three laws of motion, but rather deduced them from a multitude of experiments performed by other scientists, especially Galileo. Galileo died the same year Newton was born. These laws were truly fundamental, for they cannot be deduced or proved from other principles. Newton's laws are the foundation of classical mechanics, also called Newtonian mechanics. Using them, we can understand most familiar kinds of motion. Newton's first law, usually called the law of inertia, is a restatement of Galileo's idea that the force is not needed to keep an object moving. Newton's first law states that every object continues in a state of rest or of uniform speed in a straight line unless acted upon by a non-zero net force. Simply put, things tend to keep on doing what they're already doing. Objects in a state of rest tend to remain at rest, only a force will change that state. For an object in motion, in the absence of forces, a moving object tends to move in a straight line indefinitely. For instance, if you toss an object from a space station located in the vacuum of outer space, the object will move forever due to inertia. Thus, in Newton's first law, the net force is zero if the object is at rest or moving at constant velocity in a straight line, unless an external force is acted upon it. The amount of inertia an object has depends on its mass, which is roughly the amount of material present in the object. Mass is a measure of the inertia of an object. The more mass an object has, the greater its inertia and the more force it takes to change its state of motion. Inertia is directly related to the mass of an object. For instance, an 80-kilogram human has a whole lot less inertia than a 3,000-kilogram elephant. The elephant takes a lot more force to start or stop moving. Mass is often confused with weight. We often determine the amount of matter in an object by measuring its gravitational attraction to Earth. However, mass is more fundamental than weight. Mass is a measure of the amount of material in an object. Weight, on the other hand, is a measure of the gravitational force acting on the object. Mass and weight are proportional to each other in a given space. but they are not equal in each other. In the same location, twice the mass weighs twice as much. Some applications of the law of inertia are: when a stationary bus starts to move forward with an acceleration, the passenger is thrown backwards. When a moving car stops suddenly, the passenger lurches forward. Thus, wearing a seatbelt is necessary. Next, when the cardboard is pulled away quickly, the coin resting on the cardboard drops straight into the glass. And fourth, stationary ball only moves when kicked. Newton's second law of motion is also known as the law of acceleration. It states that the acceleration produced by a net force on an object is directly proportional to the magnitude of the net force, is in the same direction as the net force, and is inversely proportional to the mass of the object. Newton's second law describes the relationship among an object's mass, an object's acceleration, and the net force of an object. By using consistent units such as newtons for force, kilograms for mass, and meters per second squared for acceleration, we get the exact equation F equals m times a, where vector a is acceleration, F is net force, and m is mass. The key principle of Newton's second law is that unbalanced forces acting on an object cause the object to accelerate. For example, a net horizontal force of 4,000 newtons is applied to a car at rest whose weight is 10,000 newtons. What will the car's speed be after 8 seconds? The given values are the weight, 10,000 newtons, force, 4,000 newtons, time, 8 seconds, initial velocity is 0. We need to find the final speed. The equations to be used are as follows. Acceleration is taken from the formula force is equal to mass times the acceleration, and deriving the formula for acceleration, acceleration therefore is equal to force divided by mass. Substitute the formula for mass. We have acceleration is equal to force divided by weight over acceleration due to gravity. The last equation, which is the equation for the final speed is equal to initial speed plus the acceleration times the time. Now, to find the acceleration, we just substitute the given values to the formula, and we'll obtain acceleration equal to 3.92 meters per second squared. Now, to find for the final speed, just simply multiply the obtained acceleration, which is 3.93 meters per second squared, times 8 seconds. Therefore, the final velocity or the final speed is equal to 31.4 meters per second. Newton's third law of motion is also known as the law of acceleration. It states that whenever an object exerts a force on a second object, the second object exerts an equal and opposite force on the first object. Newton's third law describes the relationship between two forces in an interaction. One force is called the action force. The other force is called the reaction force. Neither force exists without the other. They are equal in strength and opposite in direction. They occur at the same time. For every action, or rather in every interaction, the forces always occur in pairs. You push against the floor, and the floor simultaneously pushes against you. The tires of a car interact with the road to produce the car's motion. The tires push against the road, and the road simultaneously pushes back on the tires. When swimming, you push the water backward and the water pushes you forward. An example of action and reaction on different masses is when a cannon is fired, there is an interaction between the cannon and the cannonball. The force the cannon exerts on the cannonball is exactly equal and opposite to the force the cannonball exerts on the cannon. The cannonball moves so fast compared with the cannon. According to Newton's second law, we must also consider the masses. The cannonball undergoes more acceleration than the cannon because its mass is much smaller. The force represents both the action and reaction forces, the larger mass of the cannon and the smaller mass of the cannonball. Using Newton's third law, we can understand how a helicopter gets its lifting force. The whirling blades force air particles downward. That is a reaction. The air forces the blades upward, and that is the reaction. This upward reaction force is called lift. When lift equals the weight of the craft, the helicopter hovers in mid-air. When lift is greater, the helicopter climbs upward. That ends our lesson for this week. I'll see you next week. Good day.